Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Exploring Rocky Worlds on the Precipice of a New Frontier. Hold on a second. There we go. Sorry, I had a computer malfunction to my left here. All right. I am Dr. Frank Summers, your host, an astronomer in the Office of Public Outreach here at the Space Telescope Science Institute. I want to thank our amazing tech team, Thomas Marufu and Grant Justice, for not only creating this the webcast, but also streaming it live to YouTube. As a reminder, we will continue to be online only throughout 2023. Our upcoming talks on May 2nd, Galaxy Clusters / Frontier Fields. Amanda hasn't given me an exact title yet, but her topic are these huge clusters of galaxies that cause gravitational lensing, okay? The largest bound structures in the universe. And she will discuss those in May. In June, we have a very special presentation. We will have a science conference for the Roman Space Telescope in June, and they have brought in some special speakers for that conference, and they will have speakers speaking on the Nancy Grace Roman Space Telescope, but they haven't given me the full list of speakers yet. One of them will be, I believe, Joan Gordon, who will talk on the history of Nancy Grace Roman herself, and the other speaker, who is as yet undetermined, will be speaking on the science that will be done with the Roman Space Telescope. So I'll have more information for you next month as that gets firmed up. But since it's going to be held during the conference, it is not going to be on the first Tuesday like our usual talks are. It's going to be, I guess this is the third or fourth Thursday, June 22nd, and it'll be held at 4:30 p.m. to coincide with their conference, so their conference attendees can actually be part of it. And then in July, we have our infamous TBD for title and TBD for speaker, which means I haven't corrected somebody for the July talk, and actually I might be giving that talk myself, speaking on one of our visualization projects. Stay tuned. How do you stay tuned, you ask? Well, you can go to our website, www.STScI.edu/public-lectures. That's where you'll find this webpage. In the lower left, you'll find a link to our webcasts, both our STScI webcasting as well as the playlist on YouTube. And if you want to get our announcements in the lower right, you can enter your email address and hit that subscribe button. Also on that webpage, we have a list of our upcoming lectures. And once a lecture has happened, you will get the information about it, the title, the description, the link to the STScI webcast, and the link to the YouTube webcast. As I said, we have an email list for the announcements that you can sign up on our website. Another way to get notifications is to subscribe to our YouTube channel, youtube.com Hubble Space Telescope, all one word. You'll get the notices of new videos as well as reminders of live events such as this. And if you have comments or questions, you want to send me an email and tell me what we did right, what we did wrong, what you'd like to see, send it to publiclecture@stsci.edu. I also would like to mention that we have social media. We do social media for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute. And here are the handles on Facebook, Twitter, YouTube, and Instagram. Your host, me, is not a social media maven. I only do a tiny bit, mostly actually about the public lecture series. But if you want those notices, you can follow me on Facebook as Dr. Frank Summers or on Twitter at Dr. Frank Summers. The news from the universe for April 2023. Our first story tonight, stormy times on Jupiter. We are going to be talking about the OPAL program, the Outer Planets Atmospheres Legacy Program. And this is a multi-year program that has been running on Hubble. It's Amy Simon and collaborators, and you can see that the original paper was out in 2015. And so each year they get, as Earth swings by the outer planets, Jupiter, Saturn, Uranus, and Neptune, they get Hubble's best images of those planets in order to study changes in the atmosphere. And this time, we're going to take a look at the recent images of Jupiter. So here is an image of Jupiter from November 2022, all right, when Earth swung past Jupiter in its orbit, because Earth is moving faster than Jupiter. Jupiter's moving slow and Earth is moving fast. And so as Earth comes by, they're at their closest, okay? And one of the things you notice about it is you notice that black spot. Why is there a spot? Well, that's because there is a moon in this image as well. That is the moon Io, the innermost of the Galilean moons of Jupiter, and that is its shadow cast on the atmosphere of Jupiter. So that's definitely a change in Jupiter's atmosphere, but it's periodic, okay? Actually, it's kind of, kind of cool that if you lived on Jupiter, you'd get a lot more solar eclipses because, Io goes around and that shadow goes across the face of Jupiter mostly every time that Io goes past. So, they get a lot more total solar eclipses than we do here on Earth. Okay, but that's not what we're looking about. We're looking at the atmosphere, and we compare how the atmosphere changes. And we also got this image from January 2023. And you can see that Jupiter is changed by getting smaller, huh? Somehow, unlike the rest of us, it lost weight over the holidays. No, that is a joke. This is actually just due to a change in perspective. So here is what we call the compass image. And you can see those scale bars down here and over here, all right? Those scale bars are the same, all right? And the problem is that what happened was between November and January, Earth got 20% further away. Okay, it went from like around 400 million miles to 480 million miles away from Jupiter. Therefore, Jupiter got 20% smaller. Okay, so that's why Jupiter appears smaller in the January image, because we kept him to the same angular scale. So you'll also note in the January image, there is another moon. This is Ganymede, okay? But again, that's not what we're talking about. We sometimes often get pictures of Galilean moons and we take pictures of Jupiter. It's kind of cool, all right? What we're really talking about is this stuff over here. You see all those ovals in the November image, okay? And how they're all lined up. Those are storms on Jupiter. And look at just how many of those ovals there are, especially in that linear feature, all right? And this reminds me of what happened back in 2006, 2008, when 3 storms at this latitude merged to combine and form what's called Oval BA. All right, and Oval BA is a larger storm that merged from 3 smaller storms. Okay, at the time, Oval BA was red, and it was compared to the Great Red Spot, which you see in the January image, and so we called it Red Spot Junior. And it has since then ceased to be red. So we're now back to calling it Oval BA because Red Spot Junior doesn't really make much sense. Okay, and so you can see there's a ton of storms in the southern part of Jupiter, but what's really cool is these storms in the northern latitudes of Jupiter. And this is something that the scientists that work on it call a vortex street. And it's really, really kind of cool, okay? All right, so I'm going to put some arrows here, and you can see that they've got 3 white storms. Actually, there's probably 4 or more. And then each of them have a corresponding red storm with it. Okay, and the red storms are rotating counterclockwise in this picture, and the white storms are rotating clockwise, and the 2 are sort of reinforcing each other as they spin, and you create this interleaving section of, clockwise, anti-clockwise, clockwise, anti-clockwise, clockwise, anti-clockwise. This what they call this vortex street of storms. And one of the cool things about it is that in the 1990s, these didn't exist, okay? These only have developed over the last 10 years. Now you say, wait a minute, Frank. A storm that develops over 10 years? I mean, we have storms that take maybe a few weeks or maybe a month to develop, but years? Well, considering that the Great Red Spot has been around for like almost 300 years, yeah, 10 years is a reasonable amount of time on Jupiter. So they got storms that last for years. And hence the OPAL project, by taking pictures every year, gets to monitor these and really study the development of storms on these outer planets. Our second story tonight is an outburst of a hot, luminous, and massive star. Okay, so how do we tell what is a hot, luminous, and massive star? Well, in astronomy, we use something called the HR diagram, okay, which is simply just a plot, okay? So on the x-axis is temperature, and because we're astronomers and we want to be a pain in the butt, it increases from right to left instead of the usual left to right, okay? That's the historical accident. You don't need to know why, but yeah, temperature increases in the opposite direction. And then brightness on the y-axis, that increases going up, okay? So this is just a plot, right? A plot of characteristics of stars. And naively, you would think that stars could exist anywhere on this plot. They could be scattered all over the place. But when you do the plot for the stars we observe, you actually find that they only exist in certain regions. And the main region, called the main sequence, is this diagonal line from top left to lower right. And this sequence actually reflects the physics of the nuclear fusion, the hydrogen nuclear fusion that's going on in its core. Then you have that giant sequence that sprouts off up to toward the upper right. And that actually represents the physics of what's happening in helium fusion as these stars move from the main sequence. They move from hydrogen fusion to helium fusion, and then their characteristics change, okay? So if you're looking for the hottest stars, you're looking to the left of this diagram. If you're looking for the brightest stars, you're looking to the top. So the really extreme stars are up here. They're hot, bright, and they're also, incidentally, massive. And these are really the extreme stars, and they're interesting to study because they're rare, but also because they have outbursts. They're unstable. They actually have these huge winds and can blow off their outer layers. And when they do that, they can be gorgeous, as in this image captured by the Webb Space Telescope. All right, everybody together. Ooh, isn't this gorgeous? Okay, so this is the star named Wolf-Rayet 124. And actually, Wolf-Rayet is a class of stars. And so this is in some catalog, the 124th entry in these catalog of Wolf-Rayet stars. And the stars at the center, where you see the big six-pointed diffraction spikes. Actually, it's 8-pointed because there's a little extra ones in the center. And then all this material has actually been blown away by this huge stellar wind of this very hot, bright, massive star. All right. And so the Webb Space Telescope, of course, observes an infrared light, and it has both near-infrared and mid-infrared detectors. So this image is actually composed of observations from 10 different filters, 6 filters in the near-infrared by NIRCam, and 4 filters in the mid-infrared from the instrument that's called MIRI. All right. So if we just look at the mid-infrared, you can see an interesting contrast that stars are mostly in the near-infrared, and the gas and dust is mostly in the mid-infrared. So this kind of gives you a feel for what you see in the near-infrared, what you see in the mid-infrared, because, honestly, we don't have that kind of, our eyes don't see that, so we don't really have that feel in our everyday experience. But you can start to see that by having both near-infrared and mid-infrared, and honestly, the range of wavelengths here is a factor of 18. It's from like 1 micron all the way up to 18 microns. So it's a very large range of wavelengths that you're covering to see lots and lots of different physics going on here. And we can contrast that with just looking at the visible light from Hubble compared to the infrared light from Webb. And so, as I've said many times, one of the best things we get to do now is we get to look and see what did Hubble see when Hubble looked at this object, and what does Webb see when it looks at its object, and we can try to do a comparison. And I can sort of I can blink back and forth to the mid-infrared and Hubble, and you can see some of the changes that you see by looking in these two different band passes. Yeah, kind of cool. Multi-wavelength astronomy, okay? And we are lucky here at the Space Telescope Science Institute to be the home of both of these telescopes and be able to see these different perspectives on objects in the universe. Our speaker tonight is Katherine Bennett. And let me stop my screen share. Where do I do that? There we go. All right. Welcome, Katie. Katie is not a PhD doctor astronomer yet. She's on her way to becoming it. She's in her first year as a graduate student at the Johns Hopkins University across the street from the Space Telescope Science Institute. And she is, enthusiastically volunteered to give a talk at the public lecture series. And I said, great. I love these enthusiastic talks. Her history is kind of interesting, okay, because she did her undergraduate at the University of Florida, not in physics, not in astronomy, but in exercise science. Yes, she came and then she worked in a hospital in a physical therapy department for several years, and then for some reason said, I want to go do astrophysics, okay? So she came to Johns Hopkins last year. Oh, no, actually, she went to Wesleyan University in Connecticut and got her master's degree, and then came to Johns Hopkins to do her PhD. So she has an interesting background, and I think she's going to, really hit it hard when she gets to it. And I always ask my speakers for something fun about that they've done. Well, in her travels up and down the East Coast, she has actually walked about one half of the Appalachian Trail. So she's done an awful lot of hiking out there. All right. So ladies and gentlemen, Katie Bennett.
Thank you so much, Frank. What a great introduction. I'm so excited to be here virtually with you all and talk about planets with you. So yes, I have quite an unusual background. I have yet to meet another astronomy PhD student who has a degree in exercise science. But I will just say that this has been a love of mine for my whole life, and it took a long time, past the gauge of senior year of college to quite figure out how to follow that passion. But I was able to do it, and I'm really grateful for that. And I just, want to say, if you have something that you feel like you want to do, I always recommend going for it. I couldn't be happier being here now and getting to share the work that I have gotten to be a part of. Just a couple of years ago, I was, the one watching these videos and dreaming about this kind of stuff, and now I'm actually getting to do it, and it is quite remarkable. But with that said, tonight we are going to be talking about planets, and if you don't love planets, I really hope that by the end of this presentation, I have changed your mind. I think that we really are on quite a brink of discovery with the James Webb Space Telescope. And I think that over the course of the next decade and decades to come, we're going to learn so much more than we ever thought possible, even 10 years ago. But before I dive into that, I wanted to just pause and talk about, why astronomy is so cool to be a part of these days. And Frank pretty much already summed it up for me. I mean, the information that we're getting with the new Webb telescope is just wonderful. And so I'm sure many of you have seen this image before. This is a deep field of using the James Webb telescope to look at many, many different galaxies that are across just a tiny, tiny bit sliver of space. We've gotten many, many beautiful images from the new Webb telescope recently. We see a nebula where baby stars are forming. We see galaxy mergers happening where two galaxies are coming and interacting. But the Webb telescope isn't just looking at big stars and galaxies, it's also looking at planets. And while sometimes the images are not quite as spectacular as seeing, galaxies upon galaxies, I want to try to convince you guys tonight that the information that we get by looking at not photos or photometry, but spectroscopy is just as intriguing as these images. But Webb doesn't discriminate. It looks across all planets, including those in the solar system. And so this is a beautiful image of Jupiter in the near infrared, and it looks similar to the pictures that Frank just showed, but the colors are kind of off, right? That's because this is a false color image, again, with different filters stacked on top of each other. But I just love this because you can see the great red spot, which doesn't look red in this image because we haven't colored it so, but you can see ionized gas at the poles, which correlates to Jupiter's own northern lights. And so, this is just another spectacular image of a planet here. And I'm going to be talking about some other gas giants like Jupiter. But before we kind of dive into that, let's go ahead and orient ourselves, because the universe is a pretty big place, right? So here we are. I love this image. This is an image that is scaled by size correctly, not distance. So these distances are not accurate. However, the relative sizes are. And what I mean by that is that you can see Earth as a tiny, tiny little ball right here. That is how small it really is relative to the sun on the far right. And so here we are. Now, here's the fun part. I wish I could be here in person with you guys to see your reactions, but we can all do a little pop quiz together to see if we remember our elementary school ordering of the planets in our solar system. So, are we ready? Excellent. We're going to start from the innermost planet right next to the sun. That one is Mercury. Then right next to us, our nearest neighbor, our twin planet, as sometimes people say, we have Venus. Then there's us. Earth is the third planet. Then next to Earth, the planet that probably gets the most amount of attention in the media and certainly the movies, is Mars. These are our 4 rocky planets that we have in our solar system. After that, of course, we have Jupiter. Next to Jupiter, we have big, beautiful Saturn. And then out in the outermost regions of the solar system, we have Uranus. And then you remember the last one? Neptune. Now, out on the very far left-hand side, we also see our dwarf planets. And yes, that is where Pluto is. We categorize Pluto as a dwarf planet now. It's still doing its thing, and there are others like it. So you don't have to feel too badly for Pluto. So here we are. This is our solar system. The Earth orbits around the sun, as do all of these other planets. And I would wager a guess, as most of us in school growing up, when you heard the word planets, you thought about these 8, yes, 9, including Pluto. These 9 planets, and that was all we knew. But that is not all there is to it. There are so many more planets orbiting other stars. So we have Earth that orbits the sun, but the sun is just a very average star, right? And the sun is in the Milky Way galaxy. Here's a little artist rendition of the Milky Way. And we can pretend, we do know that the sun is kind of just in the kind of an outermost neighborhood of the Milky Way. And so there are billions of stars in our one galaxy alone, billions of suns in this galaxy. But let's take a step back farther. I showed you that beautiful deep field Webb image that I'm sure many of you have seen before. We'll look at it again. All of these spots, from the one right in the center with this beautiful diffraction pattern all the way out to just these small dots that you see, every single one of them are also galaxies. meaning all of these galaxies likely have billions of stars and maybe billions of planets. We don't know about other planets in other galaxies yet, but we can only imagine what there is. We know about planets in our own galaxy. So that was a lot. I know it's hard to think about the sun and as a star and billions of stars in the Milky Way galaxy and billions of galaxies in the universe. I think it's mind-boggling, and I get to think about this all the time. But let's return home to the Milky Way. And we are here. And we're going to actually just focus on a tiny, tiny little subsection of the Milky Way, which is the region of our galaxy that we have searched for other planets around other stars. So again, today we're going to focus on exoplanets. And an exoplanet is simply a planet that orbits a star other than the sun. So we all, by we I mean, Earth and Mars and Saturn and Jupiter and all those planets that we know and love, we all orbit the sun, but we said that the sun is only one of billions of stars in the galaxy, which must mean that there are many other solar systems out there. And indeed, we know that that's true now. We know about thousands of planets now, and we'll get to the exact number in a little while. But I really just want to pause for a minute and talk about how rapidly this has happened and how quickly we're gaining knowledge. So people have been wondering if there were planets outside of our solar system for centuries. But it really wasn't until the 1900s that people started to really look into this. And it wasn't until 1995 that the first planet around a main sequence star, around a sun-like star, was actually detected. So I'll tell you guys that I'm a 1994 baby. So I was 1 year old when this happened. And that means that pretty much the whole field of exoplanets has started since I've been alive. And now so in 1995, we knew of one planet. Now we know of over 5,000. And really, this has just exponentially increased, especially in the last decade or so, with specific dedicated space missions to try to find these planets. And now we're at the point where we're not only finding them, but we are also trying to characterize them and trying to understand what these planets are like. Do they have atmospheres? What's in them? Are they big gas giants? Are they small and rocky like Earth? What is going on? And so we've basically started to discover that there is almost every possibility of planet out there. I love this image from Time magazine. This is obviously an artist's rendition imagining all of the different types of planets that we've discovered. So you see big balls of gas like Jupiter. You also see kind of these intermediate sized planets, and then many smaller rocky planets too. And so we have many questions, right? I mean, we have every question, for all of, the history of science. We've been focused on 9 planets, and now all of a sudden I'm telling you that we have thousands, and they're super far away, and we have to figure out how we can figure out anything about them. And so let's not get too overwhelmed. We'll keep it simple. And we will just ask a few questions to start out with to try to basically orient ourselves and figure out where we can go and what we can find out. So kind of the biggest questions that we are trying to answer about exoplanets are, 1, how many planets are there? What are they like? And are any of them like Earth? To start off with the first question, how many planets are there? I alluded to this earlier. According to NASA's website, as of last week, there are over 5,000 exoplanets that we've discovered. And of course, this number goes up about every week. This doesn't mean that there are only 5,000 planets. These are only the ones that we've discovered in the last 30 years. And again, we're discovering them quicker and quicker every year as our technology and our techniques improve. The mind-boggling thing to me is that we think that there are likely more stars than there are planets. We've estimated that there's at least a planet per star on average. But we are, again, uncovering more and more planets. It just seems to be a planet-filled, galaxy, at least. Now, next question. What are these planets like? Let's go back to our own solar system for a minute, just to orient ourselves and remind ourselves what types of planets we see in our solar system. So we have Earth along with its neighbors. These make up the rocky planets. And then you have the 4 big gas and ice giants. These are the 8 planets in our solar system. Now, we see that exoplanets fall both in this category and not quite in this category. There seems to be other types that we don't quite have analogous types of planets in our solar system. So this is a great little graphic from NASA that I really like, going over broadly the 4 types of planets that we can detect now. And I want to make a point that we, as humans, really like to categorize things to understand them, but it's very likely that there are no set categories, especially, say, between gas giants and Neptune or Saturn-sized planets, that there is this continuum. And we're working to understand if there are sharp cutoffs between all of these types of planets, or if they all have a common history. So if you look on the left side, you have your biggest gas giant planets. These are Saturn and Jupiter-like planets. We often, we talk a lot, and if you've ever been to one of these presentations before, or if you've seen another presentation about exoplanets, you've likely heard the word hot Jupiter. We refer to many of the planets that we've discovered as hot Jupiters because the planets that we have discovered that are this size are also orbiting very close to their host star. And that's actually just a bias in our techniques, and we can talk more about that later. But they are closer to their stars than Mercury is to the sun. And so they're very hot, and so we call them hot Jupiters. Very creative here. We also have Neptune-like planets. So these are smaller in size to our hot Jupiters, but they likely still have a lot of gas. So they're likely largely hydrogen and helium dominated. They might have ice, they might have some rock. We're not quite sure what's going on with these planets yet. And then you have your super Earths and your terrestrial planets. And really the only difference in category in these are the size that we know of yet. So we're not sure, say, if super Earths are more likely to have atmospheres and Earth-sized planets are more likely to just be bare rock. These are the types of questions that we're hoping to answer with the James Webb Telescope. So these broadly are what we like to focus on. For this talk, I'm going to talk mostly about terrestrial and super Earth-sized planets. I think that this is what gets people the most excited, but I want to make the point now, and I'm going to make it again at the very end of the talk, that all of these planets are important. We don't just want to say, okay, we just care about, searching for life outside of Earth, so we're only going to look at terrestrial planets. We need to understand the whole landscape of exoplanets in order to understand each individual one. Because if we see something on a terrestrial planet without, say, having a really good sense of its neighboring gas giant, it's hard to make any kind of deduction about what is going on. So just like we still love Jupiter in our own solar system, we must, and we still do, care about the Neptunes and the hot Jupiters in others. And of course, like I said, the final question that so many of us want to know, are any of them like Earth? And I mean, yeah, I want to know. And so do you. That's probably why you're here tonight. Now, I have to tell you that we just don't know the answer yet. We're hoping to take the first steps now with the Webb telescope, and I'll talk to you about how exactly we are going about doing that. Now, I just pulled this image up just because I love it, and I think it's beautiful, and I think that it really makes you realize how large this telescope is. So you can see these folks down here for scale. I just want to emphasize and take a moment to thank and appreciate the people who have spent the last 2 decades working to make this telescope a reality. I say this to many people, but I feel like I came into this field at exactly the right time, and I feel really grateful for the people who have put in the work for so long to get us where we are now, because I'm looking at data now that people 10 years ago wouldn't have been able to imagine that our data would have ever been this good. So this telescope is really revolutionizing the field of exoplanet atmospheres, and we are really on the precipice of a new frontier because this telescope is more powerful than any other instrument that we've ever put into space before, and we are actually able to look at rocky planets and look at their atmospheres for the very first time. Rocky planets are small, right? They're smaller than the hot Jupiters, which means that they're equally harder to see and understand what's going on. But we're doing it. And I know that you're wondering how. So now's the time where we roll up our sleeves and we take our pencils out and start vigorously taking notes. No, I'm just kidding. We're not doing that. But I do want to tell you guys about the technique that we use, because I think that it's just really cool. And 2, I think that it's very important to actually understand how, where the information is and how we get it. So the technique that I use and that many exoplanet astronomers use is something called the transit technique. So this is an image of the 2017 solar eclipse. I hope that some of you got to see the full thing. I was in Florida at that time, and it was partial, but it was still spectacular. And it's also hard to imagine that 2017 was, 6 years ago now. But during the solar eclipse, and during any solar eclipse, you have the moon coming between us and the sun. And when that happens, the moon is blocking the sun's light. So the amount of light that we're getting from the sun is decreasing, obviously, as the moon goes in front of the sun. This is exactly the same technique that we use every day to look for and characterize planets. So if you take a step back, instead of thinking of the sun and the moon, you think of a star and its planet, you can say, all right, so here we have a star in the middle, and we have a planet orbiting it. And if a planet is at just the right angle relative to its star and relative to us, it will pass between us and the star, and it will block some of the star's light. And we can measure this, and we can say that there's a planet there. And so I just wanted to pause for a second and say, too, that we measure this because when we use telescopes like the Webb or Hubble or any ground telescope for that matter too, it's no longer like that I'm going up to a telescope and I'm looking through it like sometimes you do on a cool space night, And I still love to do that, don't get me wrong. I love looking through telescopes directly. But my eye is now a lot less powerful than the computers and detectors that we use to gather our data. So everything is done digitally these days. There's nothing that my eye can really do anymore. So what the Webb telescope does is collects information about the amount of brightness we receive from a star over time. And so that's what we're measuring. So when the planet is not in front of the star, and an important caveat is if the star is a quiet star, you can have stars that are full of activity and change too, but we can just assume for now that the star is just quiet. We would assume that, the amount of brightness that we get from the star is the same over time. But then all of a sudden, as the planet passes in front of the star, a small amount of starlight gets blocked. And we see that as a dip in the star's light curve, we call this. Now this plot, I will admit, is a little deceiving because it makes it look like half of the star's brightness is getting blocked. In reality, this dip is a very small amount, on the order of 1/10 to 1%. So it's a very small dip in starlight, but we are able to measure it. And we call this dip the transit depth. So you're going to hear me use that word a lot. The transit depth is basically like the quintessential measurement that we take. And this tells us the size of the planet, right? Because if you think about it, a bigger planet is going to block more of the star's light by the very nature that it's larger, so it's covering a higher fraction of the star's disk. And so that's why it's easier to detect bigger planets using this technique. So for the longest time, and in fact the planet that was discovered in 1995 was a big gas giant, and many planets were for several years after that. And so you can see the difference. Again, this is highly dramatized, but you can see that a Jupiter-sized planet, the light curve, the transit depth, is going to be much bigger than, say, an Earth-sized planet where it just dips down a little bit. So I want you to just remember this because this is going to be very important. And again, with JWST, it's more powerful and we can actually start looking at these Earth-sized planets. Okay, but I have been kind of alluding to the fact that we don't just care about the planet's size. We are somehow getting information about the planet's atmosphere. And I'm going to talk to you about how we do that. So if you think about it, as the planet is coming in front of the star, the starlight is actually hitting the planet's atmosphere and filtering through the planet's atmosphere. So on this graphic, you can pretend that this black circle is the planet, and then the tiny blue rim around that is the planet's atmosphere. And this actually gives us information about what is inside the atmosphere, because the atoms and the molecules that exist in the atmosphere actually imprint a signature on the light that we see. So we are going to dive into how this works. Are you ready? I think so. Okay, so the reason that this works is if you think back again to, the last cool astronomy talk that you went to, or dig farther back to some lab experiments that you did in school growing up, we remember that if you split light, if you put light through a prism, it is split into its constituent colors. White light is just made of the colors of the rainbow. And why is this? Well, this is because light is a wave. I'm going to talk to you a little bit about just some terminology because, again, I'm going to use it a lot. And so light is a wave with very specific wavelengths. And so a wavelength, if you have a wave here, is literally just the distance between one crest, one peak of the wave, and the next. So the calmer the wave, if you think about the beach and everything's very calm and there's not a big windstorm or something, that would have long wavelengths because the distance between crests are big. But if you had a big old storm and things were really choppy and highly energetic, that wavelength would be shorter because the distance between the peaks of the waves would be shorter. The same is true for light, and that is the difference, say, between red light and blue light. Red light has a longer wavelength than blue light, and that is why light gets split up into its different colors. So we can see red light down here is around 650 nanometers, nm is just nanometers, versus blue or violet is all the way down to 400, that wavelength is all the way down to 400 nanometers. And so this is very critical. So light is a wave, and different colors represent different wavelengths. We often learn about this in reference to visible light, but this is actually true across the entire electromagnetic spectrum. So we have visible light up here, but as you may know, visible light is just a tiny, tiny sliver right here of the entire electromagnetic spectrum. So we have from highly energetic gamma rays down to your X-rays, just like you get at the doctor's office, into your infrared, like those cool night vision goggles, all the way into the radio, and yes, that radio. And all of these different regions of light have different associated wavelengths. All right, are you with me still? Now, this is really important because of the way that light interacts with matter. Basically, if you wanted to summarize astronomy in a nutshell, we try to figure out how light interacts with atoms and particles, and then interpret that based on what we are seeing. And so, if we had, say, an atom in a planet's atmosphere, the light is coming from the star, hitting that atom, and interacting with it. But it's interacting with it in a very particular way. And what's happening is that if you have an atom represented here by these concentric circles, atoms and molecules will absorb some of that light coming in from the star. Again, the light is coming in from the star at all wavelengths. However, the atoms are only absorbing light at very particular wavelengths, and this imparts a chemical signature. And so, if you had an observer, say on Earth, looking back at this planet's atmosphere, you would see the full electromagnetic spectrum, but you would see light being blocked at very specific wavelengths, correlating with the wavelengths that are being absorbed by that atom or molecule. And so this gives us a spectrum. And so anytime, I'm going to use the word spectrum a lot for the rest of the talk, and anytime I say spectrum, I'm just talking about the measurement of the amount of light or the intensity on the y-axis across different wavelengths on the x-axis. So we're going to look at several plots like this, and you might see different words here. You might see transit depth, you might see flux, but you can just think of this as the amount of light received. And you can see that this is just a particular example. Say hydrogen, if there was hydrogen in a planet's atmosphere, it would block light at very specific wavelengths. So you see these dips here where hydrogen is absorbing the light. Okay, so let's go back to talk about what this has to do with planets, because I know we did kind of a little bit of a deep dive into physics here, but let's bring it back to planets. So remember that the quintessential measurement that we're making is this transit depth, understanding the amount of dip in starlight when a planet passes in front of its star. But the key is that we don't just do this at one wavelength. We do it at a bunch. And that will actually change the size of the planet to tell us what it's made of. And the way this works is that we can have a planet. So here is a fancier drawing of a star with a planet in front of it. And you can imagine that that the molecules in the atmosphere are going to block light at very specific wavelengths. And so let's pretend for a moment that this green rim around here is hydrogen. Again, all of this is just hypothetical, not necessarily saying that that is where hydrogen is. That's not true. But let's pretend that this green rim is hydrogen. Now, at 2.1 microns, hydrogen all of a sudden is going to absorb the light at 2.1 microns coming from the star, and that makes the planet actually appear bigger. Or let's say at 1.8 microns, we'll call this carbon, actually makes the planet appear even bigger than that. And so this actually changes the transit depth at different wavelengths. Again, remember, because the transit depth is dependent on the size of the planet. So the key takeaway here is that the molecules in a planet's atmosphere are going to induce a wavelength-dependent change in transit depth. And we're going to do this together so you can actually really see what it looks like. So here we have our make-believe planet with our make-believe colors in the atmosphere, and here are the associated transit depths. So you can see that the orange one is the biggest, and so the transit depth is the deepest. And so what we'll do is we'll measure these three. So we'll measure the transit depth at green at 2.1, we'll measure it at 1.8, and we'll measure it at 2.3. And I'm going to give you just some arbitrary numbers here, and we can just pretend that we can just say that, let's call this 1, let's call this 2, and let's call this 4. And what we're going to do now, instead of making a plot that's brightness versus time, we're actually just going to plot these two things against each other. So we're going to plot wavelength and transit depth. And so what we'll do is we'll put transit depth on the y-axis, and we'll put wavelength on the x-axis. And so we'll do it together, okay? So if we have wavelength at 1.8, which corresponds to a transit depth of 2, so here's 1.8, and there's 2, so there's our purple, fuchsia, magenta dot. We can do the same thing with green. Green is at 2.1 microns, and a transit depth at 1, so we'll plot that green point right there, and then finally that orange point is 2.3 microns and 4, so we'll put that right there. And this is our transmission spectrum. This is what I spend my days trying to make. Now, the really, really important point that I want you to take away from this plot is that the fact that these points are not at the same depth at every wavelength suggests that the planet has an atmosphere, because it suggests that there are molecules in the atmosphere that are absorbing at very specific wavelengths, causing the planet to change its apparent size in a wavelength-dependent manner. So, you might ask me, okay, what happens if we just see this? What happens if we don't see any difference in the transit depth across all of the different wavelengths? That would suggest that the planet has no atmosphere. In other words, that the spectrum is flat, because this is basically telling us that there's nothing about the planet that's changing across wavelengths, meaning there are no atoms or molecules that are absorbing at specific wavelengths, causing specific changes. Everything is the same. So if a spectrum is a flat line, we think that it likely does not have an atmosphere, or at least not a detectable atmosphere. We'll get more into this later. Okay, so again, just to kind of summarize and make sure we're all on the same page, we can look at these transit depths at different wavelengths, and that tells us what is in the atmosphere. And we use the molecules that are in the atmosphere to then tell us about something that's in the planet, to tell us something about the planet, right? So if a planet, say, like Earth, if we were to look at Earth, we would expect to see ozone in Earth's transmission spectrum, because we know there's ozone in Earth's atmosphere. That tells us things like, we think that ozone might be a biosignature if you couple it with other molecules under certain situations. We can also say, oh, all right, I only see water on this world. Maybe this world is an ocean world. Again, we're really in the early stages of trying to go from this leftmost point to the rightmost point. We're trying to see what molecules are in the atmosphere and then interpret them based on what we know about the planet's radius and mass, and kind of create a picture of the planet. Because with all of this, we're never actually like taking an image of the planet, right? All we're getting is the starlight from the planet, which means that we right now, only have validation from these from these spectra. We can't actually take a snapshot of it like we can with Jupiter. So everyone's doing a great job. I think that we're ready to look at some real data now. I'm excited to show you this because it is beautiful. I think it's beautiful, and I hope you will too. So this is data that my friend and colleague Zafar worked on very hard last year, and it was actually presented to Congress a few months ago, so I just always have to brag about that. Presented in a good way to say, look at what the James Webb Telescope has been able to accomplish. So what you're looking at here are various light curves at different wavelengths. So this is microns or micrometers. This is, again, just a different unit of distance. And this offset that you use is just arbitrary. We're seeing them stacked on top of each other just to make a really pretty picture. But you can see this transition from the redder wavelengths all the way down to bluer wavelengths down here. And so then what Zafar did was measured that transit depth in all of these different wavelength bins, we call them, just like we did before, and he made this graph. You might have seen it before. This is a transmission spectrum of the hot Jupiter WASP 39b. And look at this. So we have, again, you can think of here just the amount of, that you can think of this as the transit depth on the y-axis compared to wavelength on the x-axis. And we can see peaks here where there's a sodium feature, here where there's a big carbon dioxide feature, and an even bigger one over here, right around 4.3 micrometers. We can also see a small bump here that we determined was sulfur dioxide, and that was the first time this molecule was ever detected in an exoplanet. And so this is a big deal because, one, it's been the widest wavelength coverage that we have ever been able to do with any kind of spectroscopy before. Hubble looks at a smaller subset of this region, but never before have we had a near-infrared detector that measures more than 1 micron at a high resolution in space. And so we are able to see these molecules for the very first time, even though we thought they would be there. So, we thought there was likely carbon dioxide in this gas giant, but nobody had ever measured it before. And so with gas giants in particular, now we're going to be able to take these beautiful spectra and really understand the physics and chemistry of what's going on and try to help answer questions like, do all Jupiters form in the same way? Do they form far away from the star and then migrate? Do they all form where they are? We're going to really work to use these planets to understand planet formation in context and to understand, if all solar systems form the same way or if there are a wide variety of types. But for now, we're going to keep going, and we are going to talk again about rocky planets, because I know that's why many of you are here, and I admit that I get very excited about rocky planets too. And before we dive into the rocky planets, I just wanted to give you one more caveat, that it's not just the size of the planet that matters in changing the transit depth, but it's also the size of the star. Because remember, the transit depth is dependent on the amount of starlight that's blocked, which is, of course, dependent on both the size of the planet and the size of the star. So if you have a smaller star, a correspondingly larger fraction of starlight is blocked. And so the ideal scenario is to have as big a planet you can around as small a star as possible. And so what this has really brought astronomers to is something that we call the M-dwarf opportunity. And to explain what that means, we're going to take a small pause, and I'm just going to tell you that there are many different types of stars. We tend to think of them all the same when you look up at the stars at night, but in fact, even with your naked eye, you can see that some stars appear to be bluish, while some stars appear to be a little bit more red. There are different types of stars which correspond to their size and their temperature. This is related to that HR diagram that Frank was talking about earlier before the talk started. So the Sun is a G-type star right here. And so it's pretty average as far as size goes. I mean, I know the O and B stars are huge, but we, as exoplanets, we don't really focus on these stars too much yet. We really focus on the M, K, G, and F stars over here on the left. And so the Sun is pretty average, but look how small these M-dwarf stars are. So M stars are the smallest star possible, which means that the data that we collect about their planets are going to be the highest quality. And so for rocky planets, we've really called this the M-dwarf opportunity, because rocky planets are really hard to detect and characterize. And so the smaller the star, the easier it is. So we're really focused here. The other caveat to that is that M-dwarfs are cooler. So the smaller the star is, the cooler it is. And that means that the habitable zones of these stars, the region around these stars that could likely host liquid water, is a lot closer into the star. And that is important because almost all of the planets we see are very, very close into the star. And that is simply an observational bias because we need to see the planet going around the star multiple times in order for it to be around a planet. So if we had a planet like Earth, that means that it would transit every 365 days, right? But the planets that we are looking at are largely transiting on the order of every 2 to 20 days. So they're much, much closer in to their host stars. But this also means, again, for M dwarfs, that the habitable zone is that much closer in. So you might have a planet that still transits its star every, say, 15 days, meaning its whole year is only 15 days, yet it's still in a region where we might expect liquid water to be. So there's one M-dwarf system that's pretty popular, and you might have heard of it. This is the TRAPPIST system. Now, again, I just want to bring this up as an example because I know it's the one that people love and get excited about. So you can see that if you compare the inner solar system here, here's Mercury's orbit, and here is this little drawing of where the TRAPPIST planets would be if you placed them around the Sun. So this outermost ring corresponds to this planet H that's all the way around here. So all these planets are really, really close to their host star. If you haven't heard of the TRAPPIST-1 system, it is a system of 7 presumably rocky planets that is pretty close by to Earth, that people have been really excited to look at for the possibility of seeing an atmosphere around them. Because these atmospheres and planets are so small, we've actually never successfully measured a molecule around a rocky planet before, and that is what we're trying to do right now. And the reason that that is the first question that we're trying to answer is that this is, now I would argue with the launch of the James Webb Telescope, we're on the road to understanding habitability. And so again, the very first question we have to ask is, do these planets have atmospheres? Do we see signs of molecules absorbing light in their atmospheres? From there, we can ask, could this planet host liquid water on its surface and be habitable? And then after we answer that question, then we can ask, does this planet have signs of life in its atmosphere? And I really want to emphasize that we are only at this first question. We are just starting to answer this first question for rocky planets. And by just, I mean like literally in the last 6 months. So I have some, I don't have an answer for you yet. We are actively trying to figure this out, but I really encourage you to stay tuned over the course of the next year, 2 years, 5 years, a decade, because I really do feel like soon we'll be able to understand the landscape of rocky planets a lot more to see, do these have atmosphere? Do many of them have atmospheres, or do many of them not? But we're going to look at an example. Don't worry, I have some information for you. And what we typically do is we want to understand these planets in the context of our own solar system so that we have something to compare them to. So usually we look at a rocky exoplanet and we say, okay, can I compare this to a rocky planet in our own solar system? So what I mean by that is that you have, say, Mercury, which has basically no atmosphere. Could it be like Mercury? Could it be like Venus and have a really, really thick atmosphere that's made mostly of carbon dioxide, that's very toxic and hot and dense? Could it be like Earth? Could it be thinner, possibly hospitable? Or could it be like Mars, very tenuous and thin? These are the usual comparisons that we make when we look at rocky exoplanets. And again, just like it's easier to detect bigger planets, it's also easier to detect thicker atmospheres because by nature they're just bigger, and so that means the signal is that much stronger. Now, what this means is that what I told you before about a flat line, meaning that the planet has no atmosphere, was kind of a lie, because it might not be that simple. The planet might have an atmosphere, but it might just not be detectable because of our data quality, because the atmosphere is too thin or too full of clouds that block signal to actually be able to detect anything in our transmission spectrum. So I'm going to show you an example of that. This is a project that I worked on in the fall. This paper was published a couple of months ago, and I'm going to show you what I mean by this. So this is a planet called LHS 475b. Yes, I know we are very good at naming things in astronomy. I can't take credit. And we can see the transmission spectrum here. All of these black points, this is our data. So anytime, in astronomy we have data, and basically all science, you have data that you then have to compare to a model in order to interpret it. And so here are all of our points, and you can see that if you just kind of take a step back and look at it, that looks pretty flat by eye, right? And especially when you plop a couple of these models on here that would predict huge features, and you say, okay, I don't see anything there, that is clearly flat. There's no atmosphere on this planet. But what if it's not as simple? What if we zoom in on this region in gray here and we plot some more models on it? And okay, so now we're zoomed in and we have some more models here. And we can see, oh, okay, what if there's water or carbon dioxide? Like these lines basically run through the data, but we can't distinguish which of these lines is accurate. And we also have, again, just this very flat line that seems to fit the data just as well. And so in this scenario, we can say that, all right, while we can rule out an Earth-like atmosphere, we're actually not sure which of these other scenarios it is. It could be that there's no atmosphere, but it could also be that there are too many clouds that block our signal, or it could be that the atmosphere is just too thin to detect. So we need better data quality to distinguish between these scenarios. For now, that means we need either different techniques that we can use with the James Webb Telescope, or more transits with the telescope to improve our data quality. And so that is where we are at right now. Where are we going? I will say right now we have no astronomer has published a paper showing an atmosphere around a rocky exoplanet, and specifically showing an atmosphere made of things other than just hydrogen. We've never detected carbon dioxide or water or methane or any of those things around a rocky exoplanet. I'm really excited at the possibility that the James Webb Telescope will be able to do that for us, but I do need to add another caveat about the M-dwarf opportunity, which is that, yes, while these stars are ideal to look at, there is a caveat that they are really, really active. And what I mean by that is that they're spewing out large amounts of high energy radiation that could actually just be stripping away all of these atmospheres. And we don't know whether this is happening or not yet. This is what we're trying to find out right now. So with that first planet that I showed you, we didn't see an atmosphere, but again, you can't draw a conclusion just based on one planet. We need to build up a statistical sample in order to say, okay, on average, rocky planets around M-dwarfs do or don't have atmospheres, or somewhere in between. So we're really trying to define what has become known as the cosmic shoreline. So this is trying to understand if there is a dividing line between planets with atmospheres and those without. And so, we want to know, does a planet have to be a particular size? Does it have to be a particular distance away from its star in order to hold on to that? And that is kind of, I think, the big question that we'll be able to answer in the next 5 years or so, or start to answer, I guess I should say. And then, of course, we all are, I think most people are excited at the idea of this burgeoning field of astrobiology and trying to understand if there is life in the universe. And I believe that we will get there, but I encourage all of you to just be patient and to be skeptical about news that you see, because people are and will be trying to claim detections that we just don't quite understand yet if they are true or not true. We're still in the really early stages, and one day we will answer this, but I don't believe that we will answer it yet. But we are actively working on it, and we are getting closer with the James Webb Space Telescope. And again, the last thing I just want to end with is to reiterate what I mentioned earlier with the fact that there are so many different types of exoplanets out there, and we don't want to neglect our gas giants for our rocky planets, because in order to understand the full story, we can't just look at a tree. We need to understand the entire forest to understand the whole landscape. And for that, we need to care about our Jupiters, we need to care about our Neptunes, and we need to care about our Earths. But this is a remarkable time that we're living in. We are able to look at atmospheres of rocky exoplanets that we didn't know existed 20 years ago. And I think that, if we do this talk again in 5 years, I hope it'll be a totally different talk and that we know so much more. But this is really, this is the start of a new frontier. And so I'm really grateful to be here. I'd just like to thank the Space Telescope for giving me the opportunity to come and speak with you guys. And I'm really excited to take your questions. Thank you very much.
All right. Well, thank you, Katie, for coming and giving your talk here today. Very pleasant to have, very wonderful to have you. And, what I liked so much about it is that, first of all, you're of the exoplanet generation.
Yes.
I mean, the fact that you were born just as the first exoplanets were being discovered, you've never been alive when there weren't planets around other stars. Okay. Yeah. Some of us remember a little bit of time in our lives before that happened, right? And so, you represent this whole thing. And furthermore, for so many years, it was always discussing these hot Jupiters or maybe a Saturn-sized planet. We were only talking about the largest planets because that's all we could really do with the radial velocity technique of the 1990s. And the dream of pushing down to rocky planet-size objects, was still just a dream back then.
Right. And
so it's not only are you the exoplanet generation, but you're moving on to the second generation, yes, sort of searching for exoplanets. So that's it's it's a symbol of progress to me.
Absolutely. And I'm going to try to live my life not taking for granted the fact that we know and can study rocky exoplanets, because I know people have dreamed about this for a long time.
I mean, I was at the American Museum of Natural History, and Neil Tyson, Steve Soder, and I did the exhibits there. And at one point, we looked at each other and said, wait a minute. We now know of more planets outside our solar system than we do inside our solar system. And that was a cool... That was a cool,
that's awesome.
Cool marking point, right? And we're trying to figure out, there's a way there wasn't a way to put it into the exhibits or anything, but it was just an interesting moment in time to go from that.
Yes,
so,
I like that.
I have some questions for you from myself, and we got some questions from the YouTube chat here.
Sure.
First one I want to ask about is mini Neptunes versus super Earth. So those planets that are in the 5 to 8 Earth mass type range, right?
Yeah.
Heidi Hamel has sometimes described them as mini Neptunes, and a lot of people describe them as super Earths. And to me, in my head, that says, all right, well, that just depends upon their density, doesn't it? Mm-hmm. If they're a low density, that would be a mini Neptune. If they're a high density, that would be a super Earth. What do we know about that class of planets? And,
Yes. So the reason that there is a question, I would argue a bigger question mark around those types of planets, is that there is actually degeneracy in the density that we measure. What we measure a bulk density, but there is kind of a region of size where that density, based on where that density falls and the planet size, it could be a small rocky planet surrounded by a big heaping wallop of gas, or it could be say more of a large ice giant with a little bit of gas. So it's that in this it's in this kind of intermediate state, we can't really tell. It could be one or it could be another, but we can't just decide based on mass and radius. You're right that you can absolutely do that with like the big hot Jupiters. You can measure mass, measure radius, and say, okay, I basically know this is a Jupiter. You can do it with the really tiny planets, the Earth-sized planets, and smaller. You can say, okay, I measure mass, I measure radius. All right, this is rocky. But there's just this hazy region in the middle where we can't quite lump them in one category or another, which is why we need to use transmission spectroscopy to see if we can see signs of molecules in the atmosphere to break that degeneracy and tell us, is it a mini Neptune or is it a super Earth? Okay.
So the error bars on the density in this mid-range are large enough that you can't really differentiate. Okay, that sounds cool. All right, Great. So I've been watching some of the chat, and I know Grant Justice has been watching it even closer than I have. So Grant, why don't you turn on your video and tell us some of the favorite questions you found in the chat tonight?
Absolutely. So, yeah, we've had a good chat tonight. I'm going to get us started with this one. So we did a lot of talk about exoplanets and discovery futures thereof, and I would encourage this this commenter to check out our video on specifically exomoons. But are a lot of the same principles applied to finding exoplanets as they are to exomoons? What's different in how you search or how you pick apart the spectroscopy to find them?
Yes. Oh, that's a fun question. So, exomoons, basically, yes, is the short answer. It is the same technique, meaning, we still use the transit technique to look for an exomoon, but what you can do is if you think about that light curve, you basically want to look at the light curve and then see if there's another dip in the light curve caused by a moon that's moving around and blocking an extra portion of the light. I would say that we are it's hazy trying to uncover an exomoon because the signals from the planets themselves are so noisy that it would be hard to then go down even smaller to try to find the moon. People are looking for sure, and we do have some exomoon candidates. We don't have any that have been verified yet, and that's mostly because the data is noisy, so it's hard to validate that. But yes, it's the same technique. It's basically you look for blips in the data where you wouldn't expect there to be blips.
Okay, and so for most of the moons, like in the solar system,
yes,
they're much smaller than their planet.
Right.
Right. Actually, Earth and our moon is an anomaly. That our moon is a significant size compared to Earth. So if it's like 1/10 the size, that's only 1/100th the blocking area,
right.
And then the planet decrement is only like 2% maybe of the light, and so
that's
then
that would be for a huge planet. Even a Jupiter-sized planet would only block 1% of the sunlight.
Okay, and then so you'd be talking 0.01%, right? For the moon.
Right.
All right. So yeah, JWST, I absolutely love the diagram you showed and just all that beautiful data lining up so nicely.
Yes.
Getting 1%, finding a 1%
right.
dip in that's got to be in the error bars
right
now.
Which is why it would be hard to do. There are some folks who are looking into atmospheric signatures from the moons themselves, but it becomes very complicated when you're trying to disentangle. You have information coming from the star that you have to disentangle from the planet. And that's hard to start with. You need to make sure that the signal you're seeing is from the planet and not the star. And then that would be a whole other added layer on top of that. If you say, okay, yes, we do think that there's a moon, so what signal is coming from the moon? But I think we will get there. But I suspect right now many of the signals of moons are just buried in the noise.
It's also a very new telescope, so I would imagine just like Hubble over time will refine those.
Exactly, yes.
Okay, this is interesting. I hadn't really thought about this one. How do you know at what angle or like at what view you are observing the galaxies, the planets, the systems?
Yes. Oh, that's a good question. I think I'm going to share my screen again for that. Is that okay?
Go for it. Yep.
Sure.
Okay, yes, let's see. Okay, can you see? All right, I'm gonna, hold on 1 second. I'll just go back to the slide first. So basically we can measure, okay. Thank you. Okay, so basically when we measure this light curve, we can measure the angle based on the shape of the light curve. Everything I showed you here was very symmetrical. Right, you know, this is a very like smooth coming down and then very flat coming over and smooth coming back. But basically, we can measure something that we call an impact parameter, which is basically just telling us, like, if we imagine this planet is like coming right in the middle, we measure the distance from the middle to the top. So the top being 1, so you can say, or if it's an impact parameter of 0, it's coming right through the middle. If it's an impact parameter of 1, it's right at the top. And we actually get that from the very shape of the light curve. So the more kind of even it is, the closer to the center it is. But the important thing here is that we can get that angle, and then if you couple this with radial velocity measurements, which is, you know, measuring the actual motion of the star moving back and forth, you can also get the eccentricity of the curve of the planet. So, you know, planets' orbits are not always totally circular, right? The planet sometimes kind of loops in more of an oval shape around a star, and based on the shapes that we see in the light curve and coupled to the radial velocity, we can get that information. So there are a bunch of different orbital parameters. We know a lot about planets' orbits. I would argue we probably know more about planets' orbits than we do about the planets themselves.
Yeah. All right, but Katie, this also brings up a special point that, you know, if that planet were orbiting in the plane of the sky, up and down, from our point of view, we wouldn't see a transit, right?
Yes.
So what percentage of orbits would produce a transit, right?
Yes.
In order to cross in front of the face of that star, from our perspective,
Right.
Is it 1 out of 10, 1 out of 100? What do you? What's the estimate there?
Yeah, that's a really great point, Frank, and thank you for bringing that up. Right, we only see planets that happen to be in this orientation. I'm sure there are many planets that we have not discovered yet because they're orbiting in our plane. In other words, they don't transit. And the answer to your question is that the percentage, the probability actually depends on how close the planet is to the star. So the closer a planet is to the star, I wonder if I can kind of do this with my hand here. If you think of like I'm not sure if this is going to work. We're going to try it.
Why don't you stop your screen share?
Oh, I'm sorry. Yes, thank you.
Stop the screen share, then we can see your hand better.
Yeah.
Thank you
now
for the
do it
reminder. Better? Okay. All right. So, you know, if I have a planet that's right here, it's basically kind of always in front of my hand regardless of the angle. But if it's all the way, say, out here, a small angle means that it's not in front of my hand anymore.
Right.
And so planets that are much so I think that like something like the Earth already, like by the time you get out to the Earth, is a very, very small likelihood of transiting. I mean, I think I don't want to quote an exact percent because I don't remember off the top of my head, but I mean, it's something like on the order of 1 or a few percent versus planets that are much closer in are closer to 50% transiting.
Right.
So that's why it's hard to look for Earth-like twins, because they're farther away and they're less likely to transit.
Great. I just want to make sure that the public understands that, you know,
Yes.
the likelihood of having it pass by in that exact plane is kind of small, and now you emphasized, of course, that, and it's even smaller the further you get away from it.
Right, exactly. And that's why we're so biased to looking at really close-in planets, because they are more likely to transit, and so we see them more frequently.
And hence an emphasis on the M-dwarf opportunity. Yeah.
Right, exactly.
Yeah.
Cool.
And it definitely makes you call back just how vast the distances are. It's hard to imagine, but when you take into context light years of distance and then like planets and transiting, yeah.
Right.
Can't even imagine.
I know.
All right, so we've had 2 really technical questions, so let's have a little easier one. What's your favorite exoplanet and why?
Oh, what is... Oh, that's a really great question. Okay, so I think that my favorite exoplanet, I feel like somebody is going to say this is a cop-out. I'm going to say one of the TRAPPIST planets, which I feel like is like saying Taylor Swift is your favorite musician, but whatever. It's totally true. She is, by the way. So I'm going to pick TRAPPIST-1H, which is the farthest out TRAPPIST planet. And so it is the planet that's like most likely to be in the habitable zone. And I think I would suspect that if we were going to like find a planet that was analogous to one of the icy moons of Saturn or Jupiter, it would be that planet. Like it's in a regime where there might be methane there. It could happen. You know, we have no idea yet. We haven't looked at it. But I think that is the most intriguing planet to me.
Cool. And of course, the follow-up question would be, did you get tickets for Taylor Swift's concert series this fall?
Yes, I did. Going to see her next month.
You lucked out on that. My daughter also lucked out. So she's
I got a shout out to my friend Guangwei. He was the one who got us tickets. So thanks, Guangwei.
All right, we're getting on in time here, Grant. So I think I'm going to one more question.
Okay, let me pick. I have two. Can I do two?
All right, let's do two.
Okay.
Katie's been really good. I don't really want to limit her, but I feel like I should.
That's fair. Okay, so question. Do you think that exoplanets can retain atmospheres close to M-type main sequence stars such as red dwarfs?
Oh, yes. I spend most of my time thinking about this question. I suspect, and this is just a guess, because again, we've only looked at a handful of them. I
was about to give the caveat. You may not have the data yet.
Right, we do not have the data yet. My hunch is that most of them are stripped and don't have atmospheres. So my hunch is that many of them are like Mercury, bare rock, no planet, and that we will see many flatline spectra in the next year or so. And that's okay, right? Because that is also, really cool to understand. And that actually, I mean, if we were to see that, if we were to just find out that this whole slew of planets didn't have atmospheres that we thought could, one, that tells us a lot about the stellar astrophysics of what's going on with these host stars and how strong the high energy radiation is coming from these. And it's also important because most stars are M stars, right? Like if we were to figure out that close-in planets to M stars don't have atmospheres, that would basically like eliminate a whole category, a huge section of planets that we thought could possibly be habitable that aren't. So it's a big, and if they do have atmospheres, then I mean, hooray, that would be awesome to start to uncover them. But I really say this because I've looked at the graphs of the relative amounts of high energy flux coming from M dwarfs compared to stars like our sun, and it's orders of magnitude higher from these M dwarfs. So it would be like going and getting blasted with like would you or I like to be blasted with XUV radiation all the time? No, we don't like our high energy radiation, and I suspect that a lot of these atmospheres don't either.
Right, and the habitability of the planets, around, if you're getting high energy radiation, I mean, we think about just the ultraviolet radiation that we worry about in terms of skin cancer and such, right? The M dwarf stars, they are very eruptive in some of their cases, such. Right. But I will say, in the lure of bad jokes, you mentioned that these flatliners would have no atmosphere, and if they're flatliners, that makes them dead planets, right?
So they don't have anything to worry about.
It's either a flat planet or a superhero origin story. One of them.
Okay.
All right. Last question.
One more.
Yes. Okay. Is it possible to look for a planet with an active molten core? Would it protect the planet with a magnetic field? Is that something that you are able to discern?
Oh,
The
yes.
chat's on it tonight.
Yes. Okay. Yes. So could we detect a planet with a molten core that would have a magnetic field? So I think one day, yes. I think today, not yet. We are actually closer to being able to detect a molten surface. So we think that some planets that are really close to their stars are so hot that their surface is actually just like pure magma. And if they don't have an atmosphere, we can actually use a similar technique to look at the composition of the surface itself and say, oh, wow, yes, this is a molten lava planet, we've started to call them. So we might be able to do that. Actually, I think we will be able to do that soon with Webb. As far as so we care about molten interiors because if a planet has a molten interior, that's what drives the magnetic field. And there are people working on how to detect magnetic fields in exoplanets, but right now, just like the start, basically gas giants are about a decade ahead of where we are with rocky planets, maybe even a decade to 2 decades ahead of where we are with rocky planets. So just like at first when we started only being able to detect large gas giants, and it wasn't until much later that we could detect rocky planets. Right now we are starting to ask this question in relation to gas giants because it will be much easier to answer it there because the signals will be larger. And then once we get a handle on can we measure magnetic fields in gas giants, then we can start to push down into the rocky planet regime. So I suspect that one day we will have an answer to this question, but I don't think that we will be able to do it in the next decade or so. But we will be able to determine if a planet has molten lava on its surface, which is also very cool.
That's a really cool substitute for anything else. Right. Yeah, I think one of the caveats we always have to remind people is that, like I showed the HR diagram in my intro talk, right? And that's a diagram of all the different types of stars, right? If you did a similar diagram for planets, a lot of it would be blank because we just don't see it. We don't have the capability to see it. Saturn has a 30-year orbit. Okay, so it's only been 30 years since we started discovering exoplanets. If we need a couple orbits in order to see a Saturn, it needs to be 60 to 90 years of observation before we really see a Saturn in a Saturn-sized orbit, even though we can detect a Saturn-sized planet. So there's a whole lot of planets that are out there that we just can't detect yet. And so that's why you are in such a growing field.
Right.
And if I were in graduate school again, this is where I'd be in exoplanets too. So, thumbs up for your choice.
Thank you. That's very validating. Thank you.
I did cosmology because it was the 90s and it was time to
also cosmology is great too. All of astronomy is great.
Leading into the cosmological constant and everything. That was some cool times to do cosmology. All right. Well, thank you, Katie. Really great look into what we know and what we're gonna know, and this tease of where we're getting through. I gotta say that WASP 39b stuff was amazing data.
Yes.
And so we look forward to many more of those things, and hopefully in your PhD thesis, some absolutely amazing discoveries. Okay.
Yes. Thank you so much for having me. It was a pleasure to be here.
All right. Well, to our audience, thank you for watching. May 2nd, Amanda Pagul will be talking about galaxy clusters and the frontier fields and these amazing largest structures in the universe. Please join us.